ready to roll.
All right, thanks very much, Roy, and thanks everyone for your time and welcome to this session on Spanner POCs. I'm Nevin Heinztze. I'm a senior engineer at Google on the Spanner team. So today we're going to discuss how to plan and run a Spanner POC, and the talk is roughly in 3 parts. First, we'll talk about POCs in general, why you want to do a POC, what would you learn from it, what are some of the typical goals and how you plan one. And next, to make this a bit more concrete, I'm going to walk through an example of some typical steps in a POC. I'm going to use this using a sample gaming application that's loosely based on NFL fantasy football. And then part 3, I'll conclude with some observations on best practices and tooling, and then open it up for questions. All right, so let's set some context first. So if we zoom out a little, then it's useful to recognize the role of a POC as part of the big picture of a Spanner migration. So usually the POC is fairly early on in a migration. I've got on this slide a typical set of steps of a migration, and not all migrations have exactly these steps in exactly this order, but in general, this flow is pretty common. These steps are fairly independent of the source and target databases, and I'm sure for some of you, these steps will be pretty familiar. What I'm going to do is go over these steps and highlight them from the perspective of migrations to Spanner. So most migrations start with some kind of assessment phase. So the goal here is to determine if the target database, in this case Spanner, is likely to be a good fit. Will it provide the necessary functionality? Will it meet cost performance requirements? How much work will the migration be? What are the biggest risks? What are the biggest benefits? So the next step is often a proof of concept. And in many ways, this is like an extension of the assessment. So it's typical for the proof of concept to focus on key items that came up in the assessment, like the biggest risks or confirming the main benefits can be delivered. So a proof of concept is often like a feasibility study for the full migration. We want to use it as a vehicle to understand, to explore key technical issues and trade-offs, and basically to set up a blueprint for the rest of the migration. All right. So what are the remaining steps of a migration after a POC? And I've split this into a couple of steps on this slide. So in step 3 on this slide, it's kind of the core part of the migration preparation. So design, implementation of the migration. So this can have many components. And there's some common themes here: designing Spanner schema, figuring out how to move data from your current database into Spanner, building components to support that move. And the third is application changes to switch over to using Spanner. So it's typical to prototype approaches to much of this work in the POC. Now, the next step, step 4, is testing and dry runs, and successful migrations involve significant testing, either using test traffic or parts of your production load. And it's common for steps 3 and 4 to be intermixed. So you might have an initial design and implementation, try it out, find issues, go back, do some redesign, change the implementation. So this is really an iterative process. And finally, many migrations have a kind of a target day for moving data or completing a data move and switching over to using Spanner. So this is a really critical day. It's sort of a convergence of all of the planning and execution phases of a migration. And a key part of this is knowing how to respond if things don't go according to plan. What signals and dashboards should we be looking at? What's the criteria for reverting? How do we revert? So if you'd like to hear more detailed discussion of migration, then you might be interested in the talk in previous Cloud Spanner meetup back on July 22nd on exactly this topic. But today, we're going to focus on POCs. And I'm going to start with the kind of core question: why do we do a POC? So as I mentioned earlier, in many ways, a POC is an extension of the assessment phase, a kind of in-depth, hands-on analysis. So what drives a POC is usually the open issues, items of concern from the assessment. So what you want to get out of the POC is confidence that the migration will work and that will be cost effective. So typically, you're looking to de-risk core issues. Those might be related to handling of load, performance, latency, and we'll look into this in more detail in the next slide. Or you might want to validate the main benefits you think you'll get from Spanner. So to confirm that Spanner will scale to your workload. So POCs, as I mentioned earlier, are often a mini dry run of a migration. They help identify issues you might have missed, and they provide data to better plan out the full migration. Another key role of POCs is sizing. So how large will your Spanner instance need to be? How will you manage sizing for peak versus drops in traffic and so on? So typically I'm going to have some time where I have way more traffic and at other times significantly less traffic. How am I going to manage those peaks and troughs in traffic? So data from a POC is often critical to coming up with accurate costing estimates. And finally, POCs serve to help you learn about Spanner and use it effectively. So let's talk about some concrete goals. Probably the most basic and frequent POC goal is a very fundamental one. Does Spanner scale to my use case? Now, as I'm sure many of you know, a Spanner database is not just a single machine or even a couple of machines. It's hundreds, thousands, and in some cases, tens of thousands of machines working together to provide a massive, strongly consistent database. So the ability to harness a massive machines and make them behave like one system and at the same time support serialized ACID transactions in SQL, it's really one of the defining properties of Spanner. Now, many customers want to see that in action and understand how it'll work for them, and POCs are a really good way to do that. A related question is load surges. Can Spanner scale up to surges and then scale back down again when there's less load? How quickly does this happen, and operationally, what does it look like? Next is latency. Many POCs focus on latency for key operations. They could be reads or writes, some kind of analytic queries, or a combination of all of these. And you may have particular latency percentiles that you want to achieve, maybe at 90th or 95th percentile or 99th percentile. So again, this can be another key goal of a POC. Another common question is, how many nodes do I need? So this really represents a trade-off. You can run Spanner a bit hotter and use less nodes, but see slightly higher latency and have less headroom. Or you can run Spanner a bit cooler and use more nodes, but see lower latency and have more headroom. Now, we strongly recommend keeping Spanner utilization for high priority operations under 65%, but it's not uncommon to see utilization around 35 to 50% because of the latency and headroom benefits it delivers. All right, so POCs can also be used to understand the scope of application changes that might be needed in a migration. So what code changes will I need to make to move from, say, MySQL or Postgres to Spanner? Usually the focus is on key components of an application, and the goal of the POC is to get that particular specific component running on Spanner. And the reason for doing that is we don't want to get all of the pieces of an application running during the POC, because that's just going to be too much work. Finally, a POC can be used to investigate schema trade-offs. For example, what indexes should I use? How will they impact my read latency? And moreover, how will the indexes impact my write latency? Okay, a couple of high-level comments on planning a POC. So it's really important to establish a clear scope for a POC. Don't try to address all issues or solve all problems. So it's critical to limit the scope to just several important issues, maybe 3 or 4 issues. And of course, having well-defined and realistic success criteria is important. Now, usually you want to pick a core component of your application stack as the focus of the POC. It could be your main workload, maybe your highest QPS workload, or the workload you're most concerned about for one reason or another. And that drives the implementation part of the POC. So the goal here is to get that component up and running on Spanner. Or maybe you'll build a mock of that part of the application, modeling key aspects of that application component and get that running on Spanner. The main part of a POC will typically be running this component against Spanner using sample traffic. You might have production traffic that you can replay, or maybe you already have a load generator, or perhaps setting up a load generator will be a core part of your POC. For this, it's common to use tools like JMeter or Locust as load generators. All right, we're now going to switch gears, and I'm going to make all of this more concrete by looking at a sample POC. And I'm going to use a fantasy sports game as a running example. And in particular, I'm going to base this on NFL fantasy football. I suspect some of you are already quite familiar with this, but many of you won't be. So I'm going to start out by briefly introducing some of the game structure to get us up and going. I'm then going to discuss our POC goals and describe the schema we'll use. And then I'm going to do a brief recap on some of the internals of Spanner that are going to be relevant to the POC that we're going to run. And then I'm going to discuss 3 experiments. We're going to run and discuss 3 experiments. So let's get started. So here's a one-pager on NFL fantasy football. It's somewhat oversimplified to fit on one slide, but it has the core parts of the game. So basically, at the start of the season, you as a user playing this game, you get to pick a team of 16 players, and this is usually via something we call the draft. And that's a process in and of itself, and we're not going to focus on that for the POC. We'll just assume that everyone has their 16 players. Now, the core part of the game is that each week you get to pick 9 starters. You pick a quarterback, you pick 2 running backs, you pick 2 receivers, and so on down this list. So out of your 16 players, you pick 9 as starters. So this leaves you with 7 players that are on the bench. And those 7 basically are ignored for that week. So there are some rules about the deadlines for when you have to pick your starters. In essence, you've got to pick them before they play that week. And I'm going to skip over the details of this since they aren't really important for our POC. But just note that there is a deadline, and that means we'll have frantic users making last-minute changes to their starters before the deadline. All right, so the next key part of the game is how does scoring work? So you pick your starters, and your starters are really key to this. Basically, every starter scores points based on how they do in that week's NFL games. All of this is based on the official NFL stats. And then your team score is just the sum of the scores for all of your starters. And you win that week if you score more than other teams in your league. So just a quick word on leagues. Typically, you have 8 to 10 teams in a league, or 8 to 10 users competing against each other with their teams in the league. But there are tens to hundreds of thousands of leagues. Now, every week, you can also change some of your 16 players via trading with other teams in your league. And I'm going to skip over that for the moment. We're not really going to focus on that. So there are a number of parts of the puzzle here, and we're going to focus on just one for our POC, and that's handling team updates. So as I mentioned, each week, users get to pick 9 starters. That translates to traffic each week from users to change their starters. And for example, switch in a player who is currently on the bench. And we expect to see bursts of this traffic before games start. For example, users might get fresh information about player injuries, weather conditions, actual team lineups, etc. And they'll probably want to make last-minute updates based on this new information. We're also going to assume that we're handling this for all users across tens to maybe hundreds of thousands of leagues. So as you can imagine, this is going to generate quite a lot of team traffic. All right, so let's switch to POC goals. What are we going to set as our goals for this POC. Probably the most important goal for our POC is, can we handle the expected team traffic? So let's suppose that today we see bursts of maybe 5,000 to 10,000 QPS of update team requests. And we're maybe struggling to handle those bursts. Maybe we're already running on a sharded MySQL database. So a core part of our motivation for running on Spanner is to scale easily for our future growth. Call it scalability insurance. So we could pick maybe 2x of our existing QPS burst, or maybe 5x, maybe 50x for our POC. From a Spanner perspective, it doesn't really matter too much. Internally at Google, we have Spanner databases that run many, many millions of QPS. And it's a matter of provisioning the right number of Spanner resources. For this POC, we're going to pick a 5x growth. So that means our goal is to handle traffic of around about 50,000 QPS of team update request traffic. I've added 2 other goals to our POC. First, we want to verify that our read and write latencies are in acceptable ranges. Let's say under 5 milliseconds for reads, 15 milliseconds for writes, both at median, and around about double that for 99th percentile. And the second additional goal is we want to understand how quickly Spanner can scale up if we need to handle a burst of traffic. Now, note that in Spanner, we can choose a single region or a multi-region configuration. And the main advantage of multi-region is higher availability. So you go from 4 nines for a single region to 5 nines for a multi-region. And the trade-off is cost. So a multi-region configuration is going to be more expensive. Basically, you have more replicas of your data, and writes will be a little bit slower. So for our POC, we're going to be using a single region Spanner instance. Okay, so now let's switch to our POC plan. As we've discussed, our main focus is on team update traffic, and in particular, handling bursts of this traffic that we typically see right before games start as users make last-minute changes to their starters. We're going to limit our POC to the following scope. We're going to use a population of 1 million users, randomly generated. We're going to just focus on team update traffic, and we're going to limit ourselves to looking at week 1 of the season. So we'll come back to these decisions later. The point here is that when you're running a POC, you need to fix many parameters, and at some level, they're educated guesses, and they'll often evolve during the POC, but you need to start somewhere or other to get bootstrapped. And our structure of our run, our experiments in the POC is basically 2 steps. Step 1, we're going to generate and load 1 million users and their initial teams, and then we're going to hit our database with 50,000 QPS of team update traffic. All right, next, let's talk about the tables we need to set up to run this POC. So we're going to have 2 tables. The first is a users table, and the primary key here is user ID. This table also has a user's name and email address and other information we might need, potentially including information about how they log in and authenticate to us. We're going to gloss over those. While getting the details of this right is critical for an actual migration, for the POCs, these issues often aren't our focus, and in this POC, we're going to largely ignore them. In effect, we're going to treat this data as basically a blob of a few hundred bytes that we have to carry around, but the content of these bytes isn't going to impact the running or the performance of the POC. The next table is the teams table. This is a bit more interesting for the POC. Here is where we store details of a user's team. So their quarterbacks, their running backs, their wide receivers, and also the 7 other players on the bench. Just for putting it on this slide, I've dropped some of those other fields, but we've already talked about what components we need to represent a user's team. So just slot them into the schema here. All right, so basically we need all of the information that we need to capture a user's roster in this table. Now let's focus on the primary key used by this table. First, we need to have user ID. That's pretty clear. Now, I mentioned that users play in leagues. It's possible, and it's actually pretty common, for a user to play in multiple leagues. So we're going to have league ID as a second part of the key so that we can keep track of a user's teams in multiple leagues. The third component is week. Now, the NFL season runs for 17 weeks, and well, actually it's going to be 18 weeks starting this year, plus playoffs. Now, we've chosen here to capture a user's teams for each week of the season. Strictly speaking, we don't need to do this, but it's actually a useful chunk of information to have because it allows us to track how a user changes their team over the course of a season from week to week. And it potentially allows us to do some additional validation checks and potentially some additional analytics and analysis queries. All right, 2 final points on our schema. First, I've set this up as an interleaved table. So the teams table is interleaved in the users table. And this means that a user's teams will be located together with the user's data. So it allows us to do efficient joins between these 2 tables if needed. It also allows for easy cleanup when we delete a user. All of their teams will be automatically deleted because of this clause. Now, in the particular scenario we're using for our POC today, we're not really going to be running queries where the interleaved tables are going to be important for performance. However, just note that there are many situations where interleaved tables can lead to significant performance gains, both for reads and for writes. All right, the second point I want to emphasize is on user ID. So this is a really critical part of our primary key. So user ID is here, the first component of primary key. And it's a critical part of the primary key for both users and for teams tables. Now, in the previous slide, we said we were going to use random user ID generation. And this is a really good way of achieving a uniform distribution of IDs across the key spaces for both tables. This is a recommended Spanner best practice, and in particular avoids hotspots and makes scalability easy. To explain why, I want to briefly recap an important Spanner concept, that of splits. I'm sure some of you are already very familiar with this, but as we shall see, it's an important concept to keep in mind as we're running a POC. All right. So in Spanner, the primary key of each table in a database is partitioned into chunks called splits. So in this example, the primary key is an integer, and the first split ranges from -infinity to -100, and the next split from -99 to 3000, and so on. So the same basic things happens for other types, such as strings and floats, and for multi-column primary keys. Now, each zone has a copy of each split. So each zone will have a copy of split 0. It appears in different places on different servers in each zone. But the key point is that each zone has a full copy of the key space of the table, and indeed has a full copy of the table's data. You can think of each zone as a standalone replica, and Spanner ensures that each replica stays in sync and has exactly the same committed data. So what's the role of splits? First, splits are the basis for distributing tables across span servers. And second, they form the core part of an automated sharding mechanism to balance load across span servers. So splits are not static. They're continually on the move. They're continually evolving. So for example, if a split is hot and receives lots of load and contains lots of data, it will be split into smaller splits. If 2 neighboring splits are relatively inactive for a long period of time and they're small enough, they'll eventually be merged. Now, it's worth emphasizing that the starting point for an empty table is just 1 split. So when load starts landing on that table, all of it is going to hit that 1 split. In other words, all traffic for that one table will go to just 3 span servers, 1 from each zone. Now, suppose I have 100 nodes provisioned for my Spanner instance, then my capacity when I start with an empty table is effectively 1 node out of 100, or just 1% of my total capacity. Now, the good news is that Spanner quickly adapts. It can handle 2x increases in load in a few minutes. But when starting from an empty table, we need several rounds of such increases to get to full capacity. And we'll see this process in some detail later in the talk. All right, so let's switch back to POCs. And I want to talk a bit about why splits are important for POCs. So they're really important for performance. I could have, as we've noted, splits are really important for performance. And if I have 2 databases with exactly the same data, but different sets of splits, then I'll probably get different performance. If one database just has a couple of splits and the other has a lot more splits, maybe 10x or 100x more, then we'll probably see substantial differences in performance between those 2 databases. So that means to get repeatable results in a POC, I need to set up similar splits. Or to put it another way, I need to have a warm-up procedure that I consistently use. And without this, you risk getting skewed results that are confusing and misleading. Now, as we'll see, doing a warm-up isn't that difficult. It's mostly about doing it consistently to get consistent results. All right, let's jump to some experiments. The first experiment is about scalability and latency. And we're going to start with an empty table, then load some data, and then send some team update requests. And we'll see the effect of splits. So we'll see effectively the process of doing a warm-up. The second experiment is about handling overload by scaling up. And the last experiment is about handling more expensive analytics queries that involve doing substantial scans over the database. We're going to look at the performance of such queries and how they relate to splits. And we're going to use a query to actually find out which quarterbacks are the most popular in our fantasy teams. Let's start with the first experiment. As I mentioned, we're going to start with an empty table. We're going to load some data, and then we're going to send update team requests. So the initial load happened here. The initial load was doing large bulk writes in Spanner, and they didn't really show up in the QPS. So the QPS was very small because we were sending large sets of writes to Spanner. So the QPS was probably under about 1 QPS, just doesn't show up on this graph. About 10 minutes after the load, so we did the initial load, waited for about 10 minutes, and then we started sending update traffic. And as you can see, our QPS capacity increases fairly quickly, reaching about 100% after about 45 minutes, although we do see some QPS variation. And then it becomes very stable after about an hour. And so about an hour after the start, we're reliably seeing about 56, 57,000 QPS of update team traffic. All right. Let's push this graph to the bottom of our slide to make room for a CPU graph. And when we say CPU, we're particularly interested in CPU utilization of high priority operations. So our strong recommendation is to keep this below this 65% level. Now you can see that CPU is growing over time, and that we stabilize around 42 to 43% CPU utilization. So what's going on during this ramp-up period? Well, at the start of this period, all the load is hitting only a small number of span servers, and they're likely to be running very hot. So those particular span servers are probably running at 100% utilization, and that's what's limiting our QPS. Now, many of our span servers at this point are going to be seeing little or no traffic. They're basically going to be idle. Now, the overall utilization, the overall utilization at this point over the entire instance is low. Over time, we even out the load, and more span servers see more load. And eventually this load is balanced and we see an even spread of the load across span servers. So that pretty much explains the growth in CPU utilization and how that tracks fairly closely the growth in QPS. Now, early on, I mentioned the initial load of users, and it didn't show up on our QPS graph since the QPS was so small. But we do see it on the CPU graph, and it's this little blip just before 2:30. So one conclusion here is that the initial load of user data was just a tiny blip. It didn't take long to do, and it didn't use many resources. And now we mentioned earlier we mentioned that spanner splits are done based on, the load balancing is done based on the size of data in splits and the load, basically CPU on each split. And in this case, our initial load didn't have enough data or enough CPU load and wasn't running for long enough to really stimulate these split and load balancing mechanisms. So this initial load didn't really load balance. It didn't really establish many splits. It did a little bit, but it didn't do too much. And so the real warm-up happened when we added the update teams traffic. So if our initial load had included much more data, had taken longer and used more CPU, then it's likely the shape of our QPS graph would have looked very different. And we would have seen a much faster QPS ramp up, potentially an immediate QPS ramp up. So this is something to think about for our actual migration. How much data will we be loading initially? And maybe we should model that in our POC. We'll come back to this point a little bit later. All right, let's switch over to look at latency. We've dropped the CPU graph from the top and we've replaced it with latency, but we're keeping the underlying QPS graph as a reference point. So what we see is that latency almost looks like a mirror image of QPS. Initially, latency is high and then it significantly reduces towards the end of warm-up as QPS stabilizes to around about 56,000 QPS. Let's dig a little bit deeper into this. The latency graph actually has 4 lines. It provides both 50th percentile and 99th percentile for both reads and writes. And it's the 99th percentile latency that is huge at startup. So note that the scale here is actually in seconds. So some of the latencies for 99th percentile here during startup are really huge. Now, once we reach steady state and the warm-up is complete, we see that latencies are much lower. Writes are about 10 milliseconds at median, 19 at 99th percentile, and reads are about 2 milliseconds at median and around 6.6 milliseconds at 99th percentile. Now, it's a little hard to see the behavior of latency over here, so I'm going to zoom in and just look at the latency in that chunk of the graph. So basically after warm-up is complete. So we can see a little more about what are the variations here after warm-up is complete and give a more complete picture of latency. So after warm-up, our median latencies for reads and writes, so these two, the purple line here and the green line here, are really solid at about 2 milliseconds and 10 milliseconds respectively. 99th percentile bounces around a little bit, but is mostly under 6 milliseconds for reads and 20 milliseconds for writes. So these are pretty solid numbers and fairly typical. And note that we're running here at about 43% CPU utilization. All right, in experiment 2, we're going to consider what happens if we overload the system. So we're going to crank up utilization using a warmed up database. So we've already applied our warm up procedure. We've already established all of the splits. Our database is ready to handle substantial amounts of traffic. And we're going to crank utilization up to over 65%. And we're basically going to do this by reducing the number of nodes to 12. So that's in this chunk of the graph here. We can see we're running, around about 65%, sometimes over 65% here. And then what we want to do is understand how quickly Spanner adjusts when we add more nodes. So what we're going to do is we're going to increase the number of nodes from 12 to 30. And as expected, the CPU utilization drops substantially and pretty much immediately. But we're probably more interested in the question of what actually happens to latency. So to pack all of this on one slide, we'll drop the number of nodes and we'll use CPU utilization as our reference graph and move it to the top of the slide. Now, let's add 50th percentile latency. And you can see that 50th percentile for both reads and writes doesn't actually change very much. There's a little bit of ripple here to the left when we're running at very high utilization, but mostly we're solid at around about 2 milliseconds for reads and 10 to 11 milliseconds for writes. It's a much more interesting story when we look at 99th percentile, and here the change is dramatic. When we were running at high utilization, 99th percentile latencies were up in the hundreds of milliseconds, but after the increase in nodes, they dropped back by 10x to 30x. So a couple of things to note here. First, on the right-hand side, we see that write latency 99th percentile over on this side of the graph. Write latency 99th percentile is about 2x read latency. But on the other side over here, the two latencies are actually very similar. And the likely explanation for this is that the latencies on the left are dominated by queuing effects, not on the actual operation executed. Second, note that the CPU utilization dropped when we increased the nodes, and it dropped just before about 8:15, but the 99th percentile didn't drop to a little bit after 8:15. So this 7 to 8 minute difference is basically the time for Spanner to adjust and balance the splits from hot span servers to the new span servers that we've added when we increase the node count. All right. The last experiment is a sample analytic query. And basically, we want to see which quarterback is picked more frequently. And this is essentially a full table scan and an aggregation. What we're going to do is look at the performance of this query right after the initial data load, and then again after warm-up. And a critical tool to understand the performance of these kinds of queries is the query explanations, and we'll dig into this in the next few slides. Okay, so when you run a query using Spanner's Pantheon UI, you get a page like this, and the query is here. Now, I've added an additional hint for Spanner to use extra parallelism, this use additional parallelism here. And I'll come back to this shortly. For the moment, ignore it. It actually doesn't have too much impact on the first query that we're going to run. Now, what I want to highlight here is how to get to query explanations. So when you run a query, you'll usually land on the results for that query. But to see the query explanation, you need to click on explanation, which I've circled in bright green. When you click on that, you will see an explanation panel. And that explanation panel has a lot of data, so we'll need to zoom in to see it in a bit more detail. So here we are zoomed into that panel. Now, if we focus on this panel, we see that it's made up of 3 subpanels. First, on the left, there is a zoomed in view of the plan. So we can see the serialized result at the top box of the, which is the top box of the query plan. The next is a zoomed out view that includes the entire plan, although it's kind of too small for us to really read carefully. And we can see this square here that shows what's included in the zoomed in view. Okay, and on the right is the third panel, which includes lots of stats on the query. Now, in this shade of green, I've highlighted some interesting stats. Our query took around about 321 milliseconds to run. This is 322 milliseconds to run, and it consumed about 581, just over 582 milliseconds of CPU. So how can that be? We'll dig a little bit further into the plan. And we're going to do that by basically dragging down this box and then clicking on this bottommost element, which is the table scan. So when we've done that, this is what we see. So we've dragged down the box, we've clicked on table scans. And what we see, interestingly here, is that the right-hand panel gives us the stats for the table scan. And note that there are 2 scan instances in this particular case. So these ran in parallel, and that's why the query ran for about 322 milliseconds, but consumed 582 milliseconds of CPU. It also indicates that we've just got a couple of splits in the table. So this first run of the query, we did just after warm-up. Oh, sorry, let me rephrase that. Just after we'd loaded the data, so before we did the main part of the warm-up. Now let's run the query again after warm-up. First note that the query only took about just over 100 milliseconds, and it was 322 before. Now we want to dig into the table scan operation at the bottom of the plan. And here's what we'll see. So we now have 77 executions. So there's a bunch we could discuss here. I just want to hit a few key points. So the key message is that there are more instances of the table scan operation, which means we've got more parallelism, so the query is faster. So very roughly, the more splits you have, the more table scan instances you'll see for this query. So if the latency for this kind of query is important, then ensure that your database is warmed up before you start doing performance analysis on these kinds of queries. Now, I promised before to explain a bit about what the use additional parallelism hint was about. So this hint tells Spanner to maximize available parallelism when there are lots of splits. And without it, Spanner will limit the amount of parallelism it uses. And this is really a protection mechanism to ensure that one large query with lots of parallelism doesn't monopolize the resources of a Spanner instance. But in this case, our query is not that large and we're interested in making it fast, so it's appropriate to use the flag here. But obviously you need to use this flag with care. All right, so that's all of the experiments that I wanted to discuss. But before I conclude, I want to go back to the POC plan that we mapped out at the start of our discussion and basically to do a critique of it. So here's the plan. So this is an exact copy of the slide that we had earlier in the talk. Now, some of the limitations that we have were kind of clear up front, but some of the experiments also helped us to understand the limitations of this plan and some potential things we might like to tweak if we were to do it again. So first, we saw that the million active users was kind of on the small side, and it led us to a quite small initial data set with only a few splits after the load. So part of the issue here was that in designing the POC, we ramped up the QPS. So we went from sort of 5 or 10,000 to saying, okay, in our POC, we want to do 50,000. We should probably have ramped up the number of users as well. Maybe 10 million users or 50 million users might have been reasonable. Okay, so next, let's consider the scope of the POC. So we ran just 1 week of the season, but the question is, will this work in week 18? So we'll have a lot more data in the table. Point-wise lookups should be fine, but scans will be more expensive. Finally, let's consider how we structure our runs. So basically, we generated load and then ran our team updates for week 1. But what about the rollover from 1 week to the next? So potentially, it's worth tweaking our runs so that we generate data over a full season and actually do the rollover of how the team for 1 week is essentially inherited from the team from the previous week. So the overall point here is that in a POC, we typically make simplifications of the production system and just focus on core systems and functionality. And this is a trade-off. Fewer simplifications mean that there's more work to do, there's a longer POC, and potentially we get overwhelmed with complexity, kind of missing the forest for the trees. On the other hand, more simplifications mean we might skip or miss important issues. So it's kind of useful to list out the simplifications you make and critique them. So I've listed a number of the simplifications we made in the POC here, roughly in order of importance. We've already talked about some of them, but one of them I wanted to mention here is that all of the latency numbers we were measuring were measured at Spanner, and probably we should be measuring some of those latencies both at the application as well as potentially at the user side. All right, I want to briefly recap some of the best practices we've discussed. So the first is, to collect reliable and repeatable results, make sure that your database is appropriately warmed up. It's good to have a standard warm-up procedure and to use this regularly as part of your experiment protocol. Secondly, don't run Spanner or your apps too hot, especially if you're taking latency measurements. So in general, we recommend sort of 40 to 50% as a good target for Spanner utilization. And third, get familiar with query explanations. These are a really effective tool for debugging and understanding query performance. Okay, I want to make one final comment on tooling. And it's fairly common in a POC to use data from an existing database and bring that into your POC. And we've built a tool to help you move such data sets from MySQL or Postgres to Spanner automatically. It's called Harbor Bridge. And in our POC, we could have used this to move over a set of users and their teams from an existing database to Spanner instead of randomly generating them. So Harbor Bridge provides the following functionality. It ingests data from MySQL or Postgres, either using dump or directly connecting to your database. It builds a Spanner schema automatically, and this is something that you can browse and customize using the schema assistant mode of Harbor Bridge. It creates a new Spanner database with the schema and populates it with data from the source database. And it also documents what it did with a detailed assessment report. So it identifies issues, tells you about features that weren't mapped to Spanner, and it tells you about any errors that are encountered. All right, let me stop here and take any questions. Let me check. Let me check on the, let's see, on the chat. Where are we? Okay. So Tiago asked, okay, why is this only reflected in the 99th percentile? Tiago, do you mind clarifying that question? Do you mean,
yeah, sure.
Why is, yeah, go ahead.
So yeah, I was asking about when you reduce the number of nodes, you kind of saw the effect only on the 99th percentile, but not on the other percentiles. So I was wondering, why is that only reflected on the tail indices?
So basically, when you're running a system very close to its limits, many operations are still going to perform okay, but occasionally there are going to be some operations that are going to get caught up and, basically get descheduled or don't get scheduled at an appropriate time. Because the system is basically really, really close to the limit. So it's not uncommon for your typical operation to still run fairly quickly, and it kind of depends on the queuing model, and it depends on lots of other things. So, for instance, if all queries had to go through a FIFO queue that was centralized, then we kind of expect that queuing latency would show up for basically all queries. But that's not the way that Spanner works. Spanner, you basically are sending queries across, a whole lot of different span servers, and there's going to be slight variations in the loading of those different span servers, and so many of them will be, perfectly fine. They'll be at maybe 50-55% utilization, maybe 60%, and they'll be able to handle your load just fine. Some span servers might be up, at 70-80% utilization, and maybe many of the operations on those will be, will be slower. So if we push the utilization up, to 80 or 90%, then I'd expect to see that, the latency at 50th percentile might start getting affected, or at least the latency effects of the overload would start pushing down to lower percentiles.
Okay. Yeah, that answered my question. Thank you, Nevin.
All right. Any other questions?
Maybe I can ask something else.
Absolutely.
Did you ever face a situation where a customer would like to model a larger part of the application, not only kind of this small scope? And how do you deal with that?
So I wouldn't say we've modeled just a small part of the application. This is really a critical part of the application. So and I think it's quite common to pick one of the most important workloads in your POC. So something that is highest QPS, most latency sensitive, most important for users, for example, most important part of user experience. So I wouldn't say we pick a small part. What we're trying to do is pick probably the most important part.
Yeah, wrong word.
Yeah. I just want to emphasize, we're not trying to make this problem really, really simple. We're trying to pick perhaps the hardest problem and then go dig into that. I think the challenge of picking too many problems is that the POC can stretch on for an extended period of time. But maybe that's appropriate. Maybe there are 5 or 6 issues that you really need to drill down into. So at some level, a POC can almost morph into the actual migration, and sometimes you don't really know where the POC ends and the actual migration starts. But my feeling is that you're much better off having a fairly well-defined POC, picking what you think are the really critical parts of the system to model, and just focusing on that. There's nothing. What would you say? If a customer particularly wants to model many parts of the system, then sure. I mean, that's something that we would always support them with. But it potentially can consume a lot of resources and take a considerable amount of time. So, it's all about focusing on what's the best value for the time and investment you want to put into the POC.
Got it. Thank you.
All right. Any other questions?
All right, looks like there are no other questions. So I want to thank you very much, Nevin, for hosting this session. And thank you, everyone, for joining. I will end the recording right now. Thank you all. Have a great morning, afternoon, and evening.
Thank you very much, Roy.
Thank you.